Okay, so we're going to calculate the moment of inertia of a rod, okay, when given a mass density function. Well, we've done some problems, and hopefully you've looked at some problems where there was some sort of a rod that was uniform, where it was just like a straight rod, like a baton or something like that, or a pencil, something where it was uniform all the way through. In other words, for every inch of the pencil you had, it's the same mass of the rod. But are rods always uniform? I think it's pretty clear the answer is probably not. There's tons of examples of things that rotate that aren't uniform. I mean, there's a plane wing. Plane wing you can see as you go from section to section is not uniform. You can say, well, a plane wing doesn't rotate, but it does get a torque on it as the plane shifts its direction. Spoon is clearly not uniform as it rotates. It's going to have more mass on one part than another. And a bowling pin, I mean, it's a pretty obvious one. Okay? That these are objects that are not going to be uniform. So having a uniform rod is not always like the most useful way to think of things. Now, how do you deal with it? That's the toughest question of all. Okay. Well, we know the moment of inertia integral is the one we've looked at before. Sorry about the little squares, it's just an editing thing. The integral of r squared dm. There's lots of ways to go about this. That's the simplest version of it. The integral of r squared dm is the way that we've done it. And when it was uniform, it was actually pretty easy to do. Okay. What we did is we just took the dm was just going to be the mass divided by the length, the mass density, which is going to be a constant, times dr. Okay. Dr is going to be the operator as we moved along the rod from the point where it was rotating to somewhere else along it, to whatever point r we're looking at, from 0 out to that point r. We're going to have that dr to let us know where we're integrating with respect to. So we got to put that in, and that's what we did when it was uniform. Okay. Well, there's lots and lots of examples of things that are not like that. Okay. So we're going to look at an example of a non-uniform mass density, whereas r increases, m increases linearly. Sorry with the little L there. Apparently I didn't group all my stuff together very well. You can see this example. It just looks like a little wedge. Okay, as at the pivot point, that little black dot, it's going to have a mass of 0. The mass density is going to be 0. It's going to be basically nothing there. And then as it moves away from that, as r increases, the mass density is going to get bigger, and that's why it gets wider, where something it's made of like some uniform material, and it's going to have a length of L as it goes. Okay. Now the sample function for that is going to be lambda with lambda of r equals omega r, capital omega r, and the units are going to be kilograms per meter squared. Why those units? Because if you multiply that times r, you'll get kilograms per meter, which again is going to give us a mass density, the mass per unit, the kilograms per meter. That's why it has the unit it does. The unit itself won't be by itself the mass density. It'll be times whatever function there is. It'll be the mass density. So what are the steps to actually use that function to calculate the moment of inertia? Well, the steps are pretty easy. We're going to substitute the function for dm, and then we're going to integrate the same way we did before, except just like when we used mass density of the mass divided by the unit length. To use that function, we have to put the operator for the radius variable, like dr, like we had before. We're going to have to insert that with it as well. Otherwise, it doesn't work. We don't know what to integrate with respect to, so we can't get the integral that we're looking for. So let's go back to the function that we had earlier, the one with the little wedge-looking thing, where we had a lambda r equals omega r, and we're going to start from the point where it's spun from the edge, from the narrow end, and we're going to find out what the actual moment of inertia was. Start with our old friend, I equals r squared dm. Okay. Then we're going to substitute our function in for dm. We were substituted in, and we replaced the operator with dr. We noticed that we put our units, or our limits, as 0 and L, just the way we're supposed to. We moved things around. We combined r, so we have r cubed. We moved lambda outside because it was a constant. And then we're going to take the integral of r cubed with respect to dr, That's going to be r to the fourth over 4. We're going to substitute L and 0 in as our limits, and we're going to get our magical final answer. I equals omega L squared, or L to the fourth, over 4. Okay. Well, it certainly makes sense logically. Okay, but we don't have any real good way to test it except maybe to look at the units. That's actually a pretty good way. So let's start there. Okay, well, we've got omega up here. That's over here. And they told us earlier that our units for it were going to be kilograms per meter squared. Okay. And we've got L to the fourth also. That one is right here. And we know its units are going to be meters to the fourth. And when we multiply those together, we're going to end up with kilograms meter squared. And that's exactly the kind of unit that we're looking for when it comes to moment of inertia. Okay. So that worked out great. Okay. Now we can use any function that we like the way that we have here. Okay. And we can find moment of inertia in any different way that we need to find it.